Hello, student. Welcome to this topic of time-dependent perturbation theory, which is a chapter in quantum mechanics. As you know, the perturbation theory. There are two perturbations. One is the time-independent perturbation theory, and another one is the time-dependent perturbation theory. In the time independent perturbation theory, the Hamiltonian of the system is independent of time, whereas in a time dependent perturbation theory, the Hamiltonian of the system is dependent on time. And I have also explained how the time independent perturbation theory is further classified into two categories. There are two categories of time independent perturbation theory. One is for the uh, non-degenerate case, another one is for the degenerate case. So in case of non-degenerate case, all the eigenfunctions, different eigenfunctions will have the different eigenvalues. If that is the case, it is called as the time independent perturbation theory for non-degenerate energy levels. And if different eigen wave functions have the same eigenvalue, then it is called as a degenerate case of the time independent perturbation theory. They are all the basics you have studied, and now I am concentrating on only the time dependent perturbation theory. The time dependent Schrodinger equation of systems whose Hamiltonian is independent of time is separable in spatial and time coordinates, and their eigenfunctions are of the time are of the form psi of r comma t is equal to psi of r into exponential of minus I e t upon h cross. So this is the wave function, which is a function of the position and time. And this wave function is the function of is the wave function of the particular system, but this is the wave function of the whole system. So this psi of r satisfies the time independent Schrodinger equation. This one. So this is the wave function actually, which is uh, connected to the time independent part of the Hamiltonian, and because of that reason it satisfies the time independent Schrodinger equation. And this time independent Schrodinger equation is given by h psi of r is equal to E psi of r. So this time dependent part of the eigen function disappears when we consider the physically relevant quantity psi square, which is the position probability density. That means when you are studying the time independent Hamiltonian of the system or a system, and if when you are concentrating on the position of the system, then you are actually neglecting the time dependent properties of that particular system. And this is because of the Heisenberg's uncertainty principle, as the principle states that you cannot simultaneously study the position and momentum, or the position and time of the system at a time. That is your limitation. So because of this reason, this time dependent part of the eigen function disappears. Means you are neglecting when you are concentrating on this quantity psi square, which is the position probability density. That means you are interested in the position position probability of the system, and also the expectation values of observables are also constant in time. That means uh, when you are uh, when you are more concentrating on this position of the system, the expectation values are also independent of constant. In other words, we can say that you are studying or you are dealing with the quantum statistics. So that is why in quantum statistics the time is neglected, and the system status will be, we assume that the system status is not changing over the period of time, it will be as it is. So that is the quantum statistics. But in a large number of systems, the Hamiltonian may depend upon time, resulting in the presence of resulting in the absence of stationary states. So when you are here, when you are studying the quantum statistics, there will be definitely the stationary states. The stationary states are very, very important one. But when uh, the Hamiltonian becomes dependent on time, then the stationary states will disappear. This is referred as a quantum. This is referred as a quantum dynamics. That means you are studying the dynamics of the system. So dynamics means the properties of a system are changing with respect to time. In such systems, the Hamiltonian is of the form h r comma t is equal to h naught of r plus h dash r comma t. So this is the expression for the Hamiltonian of the system, total Hamiltonian of the system. This consists of two parts. One is the time independent part, and another one is the time dependent part. So these are the two Hamiltonians. H naught r is the time independent part of the Hamiltonian, and h dash r comma t is the time dependent part of the Hamiltonian. In all perturbed systems, we assume that h dash is very, very less than h naught. In the last session, I have told or I have explained what is the meaning of perturbed system, or what is the meaning of perturbation. The perturbation means there is the change in the properties of a system. For example, you may consider the potential of a system. If the potential of a system is changing with respect to time, that is nothing but the perturbation existed in the system. So, but however, we assume that h dash is very, very less than h naught. That means in this equation 3, even though this h dash is there, it is a very, very small part as compared to this time independent part of the Hamiltonian. So that is why always we assume that h dash is very, very smaller than h naught. Then the time dependent Schrodinger equation is given by I x cross dou psi by dou t is equal to h r comma t, and psi of r comma t is there, and where this Hamiltonian h r t is given by the equation 3. Let psi n of 0 where n is equal to 1 comma 2 comma dash 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 be the stationary states eigenfunctions of the unperturbed Hamiltonian H naught, because stationary state means, as just now explained, they will be present if the Hamiltonian is independent of time. So then that is called as the unperturbed Hamiltonian. So that is why these are the stationary states eigenfunctions of the unperturbed Hamiltonian H naught, forming a complete orthonormal set. And these orthonormal set means they are the functions which are orthogonal to each other and are also normalized or called as the orthonormal functions. And these sign of zeros are of the form sign of 0 is equal to sign of 0 exponential of minus I e n t upon h cross. So this 0, here this n represents the state. This is the wave function, and now you are in the state n, and this 0 refers to the ground state of the state n. So that is the meaning. And n is equal to 1, 2, 3 gives the excited states. And this equation obeys this equation I h cross dou psi n 0 by dou t is equal to h naught psi n. So in the presence of the perturbation h dash t, the states of the system psi of r comma t in equation 4 are not the eigenfunctions of the perturbed system, and hence they can be expressed as a linear combination of psi n of zeros. So this expressing the linear combination of psi n of 0 is possible only if the eigenfunctions are pertaining to the time independent part. Otherwise, if the eigenfunctions are connected to the perturbation, they cannot be expressed as a linear combination. So that is the point. So here in this case, these eigenwave functions are not connected to the perturbation h dash. So therefore, I can expand them, or I can express them as a linear combination as below. So in quantum mechanics, the linear combinations of the wave functions. So here, these wave functions are expressed as a linear combination. This is the summation over n, and this Cn of t is equal to, that is C1 n is equal n takes a 1, 2, 3 value. So all these are called as the expansion coefficients, and I am substituting this psi n of 0 from equation 5. So this equation becomes psi n summation over n Cn of t, and now this n of 0 is n of 0 or exponential of minus I e n t upon h cross. So just as substituted the equation 5, and these Cn of t's are called as the expansion coefficients. And now we have to substitute the equation 3 and 7 into 4. So this is the equation 4. In this equation 4, I am substituting equation 3 and 7. So equation 3 is for the Hamiltonian, that is h is equal to h naught plus h dash. So this is equation 3, but psi of 40 is given by equation 7. So that is substituted here. This is equation 7, and equation 7 also comes to this side also. On both sides, I am substituting equation 7. So this is the equation obtained after substituting the equations 3 and 7 into 4. We drop the term h naught in our equation, as it belongs to time independent part of the Hamiltonian. So here in this bracket this h naught is there. This I can drop it because it is the time independent part of the Hamiltonian, but we are studying the perturbation which is time dependent, so I can drop this one, and thus all the terms in the above equation becomes time dependent. Therefore above equation becomes, so our equation becomes, just I'll drop this and I will rewrite this uh, like this. So I dropped a h naught here, and this is the remaining part of the equation. And now I multiply equation 8. Let this is the equation 8. I will multiply the equation 8 by a k bra k by left. It is a left multiplication because in this vector multiplication we have to specify whether it is a left multiplication or right multiplication, and this is the left multiplication using the direct notation, and using the orthonormality of states, where this k where this k bra k is actually a wave function, psi k of 0 exponential of I e k t upon its cross, and this orthonormality function is kn is equal to integration over psi k psi n of g2 is equal to 1. And these psi k and psi n are two states here, and which are and psi k, actually the psi k is the complex conjugate of psi n, or we can say that the system the system is initially in the state n, and now it is moving to the state k, and using direct notation, it is a left multiplication. So you have multiplied this bra to this equation by left, means you are multiplying this thing actually. So what happens on LHS side, this is multiplied to this one, and because of this normality condition that goes one, and because of this psi 0 multiplication on uh, this C and T, what happens, the system get changed or take it transition to the k state. So that is why Cn of t becomes Ck of t, and everything is written as it is. And this side here, this quantity is multiplied. Psi k of 0 exponential of I plus I e k t upon its cross is multiplied here from left. So that is written here as a matrix element, and into exponential of I into ek minus e into t upon its cross is that, because here already exponential of minus I e and t upon its cross is there. To this quantity is multiplied, that is exponential of I e k t upon its cross is multiplied. So that product becomes exponential of I into ek minus e into t upon its cross. And this psi k h dash psi n 0, psi k h dash psi k of 0 h dash psi n of 0 is written as a matrix element here, and this is equal to summation over n cn of t, and this I am writing in another short form as h dash kn, and exponential of I omega kn of t. So where this h dash kn is this matrix element, or this is equal to k h dash n, and this omega kn means it is It is ek minus en upon h cross is written as a omega k. Because actually this represents the angular frequency of the radiation emitted when there is a transition from state n to state k. Now we'll see what is the first order perturbation. Now replace h dash kn by lambda h dash kn in equation 9 and express these expansion coefficients Cn of t and Ck of t as a power series in lambda. We get equation 9 becomes like this: is cross d by dt of Ckt of 0 was there, and this Ckt of 0 is now expanded. Ah, no, is expanded like this, and on other side summation over n lambda h dash kn of r comma t is there, and cn of t 0 is also expanded in terms of lambda on RHS side into this quantity is there as it is exponential of I omega kn of t. And now I will take this lambda to inside this bracket. So this becomes a summation over n h dash kn. This thing is there. Lambda is taken inside now. This is multiplied by lambda is taken inside this bracket. So it is lambda cn of 0t plus this becomes lambda, and this becomes lambda square, this becomes lambda cube, like that, multiplied by this quantity exponential of I omega k and t. So next what we have to do, equating the coefficients of lambda raised to 0, that is 0th order, lambda raised to 1 first order, and lambda square and second order in equation 10, we get these quantities d by dt of ck of 0 to t is equal to 0, because there is no term on RHS side corresponding to this 0th order. Similarly, this is the first order, uh, the power of lambda when these are the terms equated as lambda raised to 1 terms, and these are the things equated as a coefficient of lambda square on both sides. So we got three equations just comparing the lambda raised to 0 terms and lambda raised to 1 terms and lambda square terms on both sides, and neglecting the higher order terms. So from equation 11 it is seen that the coefficient ck of 0 is constant because its derivative is 0. The derivative of the ck of t is 0, means it is a constant term. In time, it's true as the zero order Hamiltonian is time independent, because that is linked to the unperturbed part of the Hamiltonian, so its derivative is 0. And from equation 12, the first order contribution to CMC is given by equation 12. Just you integrate this equation 12 and send this IH cross to RHS, you will get this equation. So ck1 of t is equal to 1 by h cross, and this thing is that. And next, we are interested in the case where the system is initially, that is at t is equal to 0 in the unperturbed state n, so that All ck's are 0 except cn raised to 0, which is unity. So when the system is in unperturbed condition, all the all the coefficients corresponding to the state k are 0, because still the system has not taken the transition. That is why all ck's are 0. But the cn is raised to 0 is not 0, because the system is in this state only, in the state n only. And now the perturbation H dash is switched on for a time t, and its effect on the states is studied. Now the perturbation is switched on means uh, external, we may apply some external electric field, magnetic field, all those things, or you change the frequency. They are all becomes the perturbation. And for times after t, h dash is equal to 0. That means this perturbation will be on the system only for some time, that is 0 to t. And before, when time is equal to 0, no perturbation. And when the time is after t, then also no perturbation. So h dash is 0, and therefore uh, this uh, this is limited to for t only, 0 to t only, this state, for time greater than t. And now equation 13 becomes like this: ck of 1t is equal to 1 by h cross 0 to t. So h dash k, and so what I did in equation 13, this summation over n cn raised to 0 t was there, that is set into 0, because for the initial state of the system, this goes 1. This is set as a unity, and I am writing the remaining things as it is. So these are the remaining things: 1 by ih cross 0 to t h dash, that summation over n cn of t set equal to unity, and h dash kn r comma t exponential of I into omega k t to d dash. So now in place of t, it becomes t dash dt dash. So you are in some new time greater than 0 and less than t, you are somewhere in that period. So this is the time at which the system is there. And the perturbation H dash has induced the transition to other states, and after a time t, the perturbation that the probability that a transition to state k has occurred is given by ck of 1 square, means the amplitude or the square of intensity. This is the gives the intensity, or this is also indicate the probability or probability density of the system in k state. So this can be obtained even using the psi k of 1t, but since this expansion coefficient is connected to the perturbed state, and so this square of this quantity gives the probability density of the time. Hmm? So this is the time dependent perturbation theory of a perturbed system, and this can be applied to any perturbed state. Thanks for watching.